First of all, thank you very much to all of you for joining us today. My name is Sebastián Taramona. My advisors are Domingo Santana and Jesus Gómez Fernández. And today's topic is, well, the work I've been doing for my PhD thesis, the design and development of a linear beam-down concentrated solar technology for industrial applications. Once again, thank you for joining us, and thanks to everyone who has made this work possible. So, we will start up by giving a small brief down of the different topics that we'll discuss today. First, we'll give a general introduction. Then we'll get into the design process of a flat beam-down solar field. Afterwards, we'll discuss the design and development of a solar prototype of this technology. Then we'll perform an environmental and energetic analysis. After that, we'll develop a fixed bed solar drying model, and we'll finish up this thesis with the scale-up of this technology up to a commercial level and some general conclusions of this work. So, starting up with the introduction. Taking into account the goals of the Paris Agreement and to keep the temperature levels from rising above 2 degrees Celsius, one of the different sectors that we want to, or we have to tackle, is the one of the industrial sector, that considering the global greenhouse gas emissions, it accounts for roughly 24.2% of set emissions. On the other hand, if we want to see the energy demand of this same industrial process, we can see that from total final energy consumption, this energy demand for industry accounts for around 23.7%, specifically the heat demand. And if we were to look into the different temperature ranges, as it's seen on the figure of the right, you can see that between low temperatures and medium temperatures, that's up to 400 degrees Celsius, we have roughly 50% of this demand. So, one of the ways we have to supply this demand in a renewable fashion, here are some examples for the different some industries that require drying particular materials and their different emissions of CO2 regarding each ton of resulting material. So, as I was saying, one of these options that we have to supply this clean energy for in the form of heat is using concentrated solar technologies. Between them, we have, for example, solar towers that have this range of concentrations, operate at approximately 565 degrees Celsius, and have around up to 35% annual to solar to electric efficiency. We also have, for example, parabolic dishes that has higher concentration ratios, which can also reach higher temperatures and also have good efficiency. These two concentrated solar power technologies, as you can see in the figure, aim all the sun rays up to a single target point. We also have two different, another approach with another two technologies. For example, the parabolic trough collectors, which instead of concentrating them in a single point, we concentrate the solar irradiance in a line. And here you can also see the concentration ratios, temperature, and solar efficiency. And finally, we have the linear Fresnel reflectors, which have somewhat similar concentration ratios, and have overall the lowest annual solar to electric efficiency. In this thesis, we'll be focusing on this final linear Fresnel option. Why? Basically, because it falls in the range between low to medium temperatures that we want to tackle, and also because it has a lower relative cost than the other technologies, and it also allows us to process the materials we want, for example, in a linear fashion. That means that the materials can enter the processing line in a, for example, wet state, and in the end of the solar field, finish heated up and dried. So, delving further into this technology, these linear Fresnel reflectors consist of several mirror rows located near the ground, as you can see in this figure. And all of these reflectors are with a slight curvature in the transversal axis. And all the sun rays concentrate the solar irradiance up in a solar receiver located several meters above them. As I previously said, the main benefits of this technology is that it's simple, it's robust, and it has lower capital costs. And, well, the drawbacks are lower efficiency and concentration ratios related to other technologies. But yeah, what happens if we want to process heavy materials? Do we take them up 3-4 meters and move them around? That's not particularly cheap, and it's a little bit costly. So we are going to propose to use this beam down approach. This approach consists of basically utilizing the optical properties of bifocal figures, such as the hyperbola you can see on the right side of the screen. And here, the interesting thing is that all of the sun rays aimed towards one of the focal points after intersecting the hyperbola will be redirected towards the ground level. This means we can locate the heavier particles near the ground. And, well, it also has the main drawback that it causes additional optical losses, a drop of optical efficiency, basically because we're casting a shade in the primary field, and also because of the magnification effect. And here you can see a beam down tower this is the Master Institute test site. So what we propose is to mix this linear Fresnel technology with the beam down approach and develop a linear beam down solar field. Here it consists of a heliostat field with several mirror rows that redirect the sun rays towards a beam down reflector, which on its own redirects them to a ground receiver. This technology was patented by the university in 2018, and the main objective of my PhD dissertation is to study the viability of this approach to supply heat for low to mid-temperature industrial processes. Okay, so once we have established the context of the thesis, we'll start with the design process of the technology we're proposing. As I previously said, the beam down basically utilizes the optical properties of the hyperbola. However, a hyperbolic mirror, it's not particularly cheap. So what we want to do instead is develop a beam down, but only using flat mirrors and all of them located at the same height. This also allows us to simplify the installation process of this beam down technology. As you can see in the figure on the right side, you can see both approaches. First the hyperbolic reflector, and then using flat mirrors. So how do we design this solar field? We have to tackle the 3 different stages. First, the primary mirrors, that are the ones located near the ground level. Then the beam down, that's the one that the improvement that we want to take into account. And finally, the solar receiver. This design process is considering solar noon for the spring equinox and always a north to south orientation of the solar field. So starting with the primary mirrors, the input parameters that we are going to consider are the width of the mirrors as well as the focal height. And what we want to obtain for the solar field is the position, the tilt, and the curvature of the mirrors. To do this, we'll be using Mather's method, which allows us to define the solar field in such a way that, as you can see in the figure, there's no blocking of the reflected sun rays towards the receiver. This allows us to, for the design conditions, to reduce the optical losses. Now, moving forward to the beam down design, to simplify the process and to make it all related to the solar field geometry, we're going to first obtain the width of the beam down mirrors. In order to do that, we're going to take the furthest away primary mirrors we obtain from the primary field design process, and we're going to intersect with the beam down height. And with the solar aperture, we're going to establish the beam down mirror width we're going to consider. Afterwards, once we have this width, we can proceed to define all of the position and the curvature of all the beam down mirrors. Here, the important things are that, one, all of the mirrors are located at the same height, and all of them have an associated hyperbola, which they are tangent at the desired height. This allows us to keep the interesting optical properties of the hyperbola, but with using flat mirrors in this case. And finally, we have to design the solar receiver. What we do in this case is we take all of the primary mirrors and simulate the aperture through the solar field, as you can see, and how they reflect up in the beam down. After that reflection, we take the furthest away spot that we can obtain, and we compare them with the solar receiver that we have pre-designed. If it fits in the spot, we consider it's okay. Otherwise, we'll have to readjust the receiver width and recalculate the complete solar field. So it will be a little bit bigger or smaller depending on the size. Now, once we have completely defined the solar field, we want to be able to characterize it and to obtain first the efficiency and then the concentration of it. In order to do so, we'll be calculating the efficiency of each of the primary mirrors and then of the complete solar field. We have to take into account all of these different parameters that I'll be explaining bit by bit. First, we have to take to consider the cosine effect of both the primary mirrors and the beam down, and this cosine effect is the relative losses with the inclination of the mirror. As well, we want to reflect the sun rays instead of directly receiving them. We'll always have some losses associated with this effect. Then we also have to consider the reflectivity of each of the mirrors. In this case, to simplify the process and assuming everything's ideal, we'll consider that the reflectivity is ideal and all of the energy that reaches the mirrors is reflected, and there's no transmissivity and no absorption either. Then we also have to take into account the blocking and shading of the adjacent primary mirrors. That means either the sun rays that could reach them but do not reach them because one of the mirrors is blocking them, or the reflecting ones that do not reach the receiver. In this case, because of how we define the complete solar field using Mather's method, for design conditions, this loss becomes negligible. A loss that is not negligible, and it's one of the most important drawbacks of this process, is the beam down shading. That's the shade casted by the secondary reflectors, as you can see in the figure, up onto the primary mirror field. And this is one of the bigger losses we have to take into account. If we also move towards the longitudinal axis of the solar field, we have to take into account that some of the sun rays might be reflected by the primary mirrors but do not reach the receivers. This is the end factor. And because of, to simplify the process, we'll assume that the solar field is infinitely long and this parameter becomes negligible, and we neglect it. And finally, we also have to take into account the spillage in the receiver zone, because some of the sun rays might be reflected up to the beam down, then once down again, and they may not reach the receiver region. But because of how we define the receiver, we're also going to assume that this parameter becomes negligible. After we have calculated all the efficiencies, we can proceed to obtain the solar concentration. First the geometric and then the mean. First for the mirrors, comparing the mirror width with the receiver width, and then with the complete solar field by comparing all of the mirrors with the receiver. In order to quantify the results and standardize them, since solar fields can be completely different from one to another, we're going to be proposing two dimensionless parameters that relate the geometry of the solar field. Here we have a basic sketch of a solar field where this is the primary mirrors, this is the focal point, and this is the beam down, and we can present two different parameters. The first is this parameter that relates the height of the focal point with the width of the, half the aperture width of the mirrors, and it gives us an idea of how tall the solar field is related to its width. And we also have this parameter that compares the beam down height with the focal height, which gives us an idea of how the beam down is located in relationship with the focal point. So this is basically the percentage of altitude regarding the focal point. And we can also represent this in a triangle. And this triangle also gives us an idea of the beam down width, which is one of the most important factors that we have to consider for analyzing the results. And for example, if we were to increase this parameter, the solar field would be higher, which means the beam down width would be higher, the other way around. And for the beam down fraction, we have that a higher fraction means a lower width, and the same thing on the other end. Lower fraction means wider beam down. So after we have defined these two parameters, we can proceed to analyze the results. First, here we have the optical efficiency of the solar field using the model we previously developed with all the simplifications. And here, as you can see, in this top right corner of the graphic, we have the better results since we have Taller solar fields with narrow beam downs, which means less shading. And here, on the other hand, we have the complete opposite results. Moving forward, we can also characterize the receiver width using this dimensionless parameter, also relating it with the aperture, total aperture width. And here we can see also a similar approach, where in this corner of the graphic, we have wider receiver widths, which is because the solar aperture has to travel further, and it gives us a bigger spot. And something similar happens in this other edge, where, while the optimal point is located somewhere in the middle with less ray aperture in a relative. Finally, we can proceed to analyze the concentration results. First, we will compare the model that we developed with all the simplified hypotheses with SolTrace, which is a specific software used to calculate these solar fields. And we can see that there's a relatively good fit between the model and the simulations. Additionally, if we were to analyze the results, we can see that in this corner we have lower results, lower concentration, because we have a wider receiver, which means the energy is more dispersed. And on the other hand, we have, well, less efficiency because we have more shading, which means less concentration. And the sweet spot is located somewhere in the middle between these 2 points. So, rounding up this chapter, we were able to obtain some pre-designed charts that I previously mentioned. So this way we can pre-design the solar field in an easier fashion. We were able to obtain a design methodology for these types of solar fields. And also, we were able to achieve concentrations, in theory, of up to 31 suns. Okay, so now we have developed a design methodology. The next step is to bring this methodology up to a lab grade. So in order to do this, we'll be designing, constructing, and characterizing a solar field prototype with this technology. Following up with the methodology I previously presented, we're going to be changing a little some details to fit the design criteria that we want for our lab. First of all, the mirrors we will be using, instead of curved ones, are going to be flat, which is basically to reduce the cost associated with building the prototype. And additionally, we also have to consider the thickness of the mirrors. Since since a solar field that uses smaller mirrors could result in some of them not being able to turn properly. So we have to take this into account to properly design the prototype. Otherwise, on the other end, for the beam down, we're going to be using the same methodology I previously explained. So this is basically the sketch of the prototype that we have designed, considering also the best conditions in terms of concentration. Here you can see that we have a primary mirror, that are divided into 4 different sets of 10 meters each. They have 5.5 centimeters wide. And here we have it, they're from one end to another of half of the solar field. They're basically 1.44 meters. We also have this beam down height and this focal height with the best results in terms of concentration. And with this, we can obtain this beam down reflector of 18 flat mirrors in total. And finally, we'll be considering a solar receiver of 10 centimeters wide. And with all of this into result and several hours of work, we were able to transform this sketch up to a real prototype, as you can see in the figure. Going into detail of the different construction technicalities of the prototype, here we can see a picture of the primary mirrors on the right side of the screen. As you can see, they are reinforced with a T-shaped aluminum profile. This is done to reduce the bending of them and to make them more leveled. And we control all of them using an Arduino Mega board with a reduction set in 1 in 100. And this is done to improve the precision of these mirrors and their tracking. Analyzing the relative results with the design, we see a maximum horizontal misplacement of around 6 millimeters from the design position, and regarding vertical misplacements, around 4 millimeters between the average position. Going towards the beam down, here we can also see in the figure that we have 9 mirrors on each side, and all of them are once again reinforced with T-shaped beams and pasted them to them. The errors in this case, the horizontal misplacement is a little bit wider. We have 22 millimeters, and the vertical misplacement against the beam down position that we wanted in this case is 10 millimeters, and the maximum angle difference between the design one and, well, the worst one is 0.34 degrees. Now, once we have this prototype built, we have to take some measurements. And what do we use to take these measurements? We're going to be using a total of 4 different sensors. First, a radiometer that's located in a Lambertian target, as you can see in the figure, in the central part of the solar field, where the concentrated sun rays reach. We'll also be using a CCD camera located directly above them. This way, we can take pictures of this Lambertian target and characterize the solar concentration profile. And this way, we can obtain how it behaves in the width axis. We'll also be using 2 pyranometers to indirectly measure the beam irradiance. That's the one that we can actually concentrate. And we'll be storing these data using some National Instruments data acquisition boards. So, once we have built this prototype, we want to characterize in further detail the behavior of each of the different components, the solar receiver, the beam down, and the primary mirrors. That's why we'll be analyzing the optical efficiency of each of the steps on their own. First, we'll be analyzing them using the simulation software, and then we'll be comparing them with the experimental results. So first, the primary mirrors, same as I previously said, it depends on the shading casted by the beam down, as well as the cosine effect of the different mirrors. On the other hand, for the beam down, in this case, since it's not an ideal version, but a real one, we might have some spillage in the sides of the beam down, as it may not be perfectly pointing towards the focal point, and there may be some issues with that. So we have to take them into account also. And finally, for the receiver, we also have to take into account this cosine effect, because the sun rays are not reaching completely vertical. Instead, we have some tilt. And we may also have some spillage because of, once again, this is not an ideal design process. And with all of these considerations in mind, we can obtain a theoretical efficiency of how the solar field is supposed to behave. Now, we want to compare this with the reality, with the measurements we actually obtain. And in this case, what we do is compare them to obtain the measured efficiency, by comparing the average concentration in the receiver that you can see in the picture of the top right, and the beam irradiance that reaches our complete solar field. Here in the picture of the top right, you can see one of the CCD camera pictures, but translating to the heat flux profile. And you can see in the figure that also there, where the radiometer is located. And once we have this measured parameter, we can compare it with the theoretical one. And this comparison gives us an idea of all those different errors between the theory and the reality, which are not easily measurable, but well, draw down the performance of the solar field. And we also have to take those into account. Rounding up the results in terms of efficiency for the different measurements that we took in our solar field, we can obtain this for each of the different sections of the solar field. The first thing that comes to the eye is that all of the 3 sections show similar results in terms of efficiency, but we have to take this with a pinch of salt, because we can see that the shading of the beam down, it's that roughly at 22% loss on efficiency of the solar field, which is an important parameter, only matched by this miscellaneous parameter that I previously defined, which takes into account all those different slope errors, tracking errors, and all those different losses that we were not able to directly quantify. So in theory, the performance of the solar field could be upgraded almost 25% by adjusting this parameter. Now, comparing going forward to the concentration profiles that we've obtained, we have these 2 figures, both for almost solar noon, and one is from the 3rd of July, and the other is for the next day. And here you can see the concentration profiles obtained with these in these two tests. You can see that we reach almost 8,000 watts per square meter. And we also have to take into account that this gray zone that you can see in the figures is because of the translation between the grayscale of the camera and these heat flux units because of the uncertainties in this translation. Now, if we were to only focus on the receiver width that we designed, we can see that we obtain an average concentration of 6.41 suns over this receiver width. Now, rounding up this chapter, we were able to design, construct, and test the first of its kind flat beam down prototype. We were able to quantify the slope and tracking errors, which relate almost to a 25% drop, and we were able to obtain the first experimental results with this technology, obtaining 6.41 suns and almost 30% of optical efficiency with this approach. Now, after we have defined this technology, we have studied it, we have obtained the best relation for the concentration ratios, and we have developed a prototype, we want to see how this technology impacts the environment, the environmental effects of this approach we're proposing. In order to do so, we'll be doing a life cycle assessment, which quantifies the different potential environmental impacts of this technology. Now, our objective will be to study the effect of the beam down fraction, the BDF, which is the height of the beam down, over these different parameters that we'll be studying, the environmental impact. And we'll be doing two different analyses. First, one that only takes into account the construction phase of the technology, and then that also takes into account the operational phase, which for this we also need to take into account the solar energy. For both analyses, we'll be considering the materials of the technology as well as the mass of each and every one of them. And for the second stage, we'll also have to take into account the solar energy we can generate with this approach. To do this analysis, we won't be using the prototype dimensions. Instead, we'll be using what would be a more industrial level solar field. That's composed in this case of 10 primary mirrors, 60 centimeters wide, and with a focal height of almost 4 meters above them, as you can see in the figure. And on the other figure, you can see what we'll be studying. That's the effect of this beam down height. In order to quantify these environmental impacts, we'll be using the standard ISO 14040 and 14044, which takes into account 4 different stages. The first is the classification of the materials we're going to be using. In this case, for the solar field, we're going to be using solar glass, silver, and aluminum, and then we'll be characterizing them. This means we will be assigning each of these materials an environmental impact, and with that we can obtain the global environmental impact of this technology. And this will be done using the ILCD methodology. Finally, we could also do some normalization and weighting, but these steps are not obligatory, so we won't be performing them. Moving forward to the construction results, here you can see in the graphic all of the results for the different beam down heights. As you can see, first for the primary mirrors, the effect of the beam down height is almost negligible, only a little bit further towards the higher beam down reflectors. This is because we obtain a wider receiver, which means we have to adjust the solar field a little bit further away. On the other hand, comparing with the beam down, you can see that the effect is the other way around. The lower the solar field, the wider the receiver we have, which means we need more mirrors, which means we need more structure, and which means we have more environmental impact. Now, going to the other phase, the operation phase, here we can see first in the picture of the right, we can see the concentration trends as well as the energy, which follow similar trends as the one I previously presented regarding especially the concentration. And in the figure of the left, you can see the global warming potential. That is one of the impacts that we're going to be studying. In this case, the best result falls in this BDF of 0.6, which means 60% of the focal height for the beam down, which falls in also on the closer to the maximum concentration we can obtain with this technology. So this is a fairly good result in terms of both of concentration-wise and in terms of environmental impact. On the other hand, other of the global impact factors that we're analyzing is the particulate matter, which in this case, it follows on the other end, which means that the process of obtaining the materials and constructing the prototype is worse in this case than the process of obtaining natural gas, which is, well, the bad result of this analysis. Rounding up this section, we were able to quantify the impact of the environmental impact of the beam down height in terms of the solar field. We were able to obtain a drop in 34% in global warming potential and 41% in also ozone depleting potential, which also followed a similar trend as the one presented in GWP. And for the best configuration, with this solar field, we would be able to obtain 24.5 suns and an optical efficiency, once again, around 30%. Moving forward, we have already analyzed the design process of the solar field. We have constructed a prototype. We have studied the environmental effects. But we want to see what happens with the energy that we're concentrating, because all of this is done to obtain concentrated energy, to process heavy materials, thermally process heavy materials. So in order to do this, we'll be developing a fixed bed solar drying model. Now, the drying process of particle materials is usually done using hot air convection, either by blowing air perpendicularly to the particle bed or in parallel. And most of the literature is focused on the two regimes that you can see in the top right of the figure, the evaporative regime, which in this case, the bed is completely saturated with water, and also the capillary regime, even though it's not completely saturated, we still have these inner flows of water and capillary effect. But these two do not match the amount of water content that we're aiming to process, as for example, the asphalt material. So in this section, what we'll be doing is developing a drying model that considers first the solar concentration as the driving motor, and then only the receding regime, because, for example, for the asphalt industry, we have to dry around 5% water content, which we do not have those water breaches and those capillary effects, and they do not apply in this case. In order to do so, we'll be developing a model which several simplification hypotheses, such as, for example, that the particles are going to be rigid spheres, that the bed is divided in two sections, both for the thermal analysis and for the mass analysis. For the mass analysis, we'll be dividing them into a dry region where the particles are completely dry, and into a wet region where the particles are still wet and the air within this section is saturated. And on the other hand, for the thermal analysis, we'll be dividing the bed into a surface layer. That's the one that receives the solar concentration and also has those associated losses, and then the inside of the bed that, it reaches it through conduction. Additionally, we have a boundary layer that divides both dry and wet region, and this layer is going to be moving towards the depth of the bed as the fixed bed starts drying down. We'll also be considering that the walls and the floor are adiabatic and impermeable, and that the solar irradiance is uniformly distributed in the surface of the bed, which is an important simplification for this process. So, first we're going to be solving the mass balances. In this case, we have to take into account the difference in densities between both sections of the bed, as well as with the exterior, the volumetric gas fraction within the bed, a dispersion coefficient that's calculated from the natural convection coefficient, assuming a horizontal flat plate in the surface, and also the distance between the surface and the boundary layer that represents the drying process. And additionally, we also have to take into account the evaporation surface that's going to be in the boundary layer, which is defined by its thickness and the specific surface of it. On the other hand, for the energy balances, we want to obtain the temperature evolution of both of the sections, the surface layer as well as the inside of the bed. So for the surface, we'll have to take into account the concentration profile, the concentration we have, the absorptivity of the materials, and the number of particles in it. And for the convection losses, we once again will be assuming a horizontal flat plate, and we'll be assuming that the particles behave as a gray irradiative body. Then we also have to take into account the conduction towards the inside. There we'll be using a lumped approach between the surface layer and the boundary layer. And finally, we also have to take into account that the water evaporation and the mass transfers with the exterior take a fraction of the heat that could be used to heat up the bed. Now, these processes, as they depend on one another, they will be solved in tandem. That way, we can iteratively solve 4 small time increments with the evolution of the bed. This means that for the current conditions of the bed, we'll be solving the mass flows and the heat flows, obtaining the next conditions of the bed in terms of mass, temperature, and properties. And with these updated conditions, we can be solving we begin to solve the process once again. And this is done up until the stopping conditions are met, which can be a specific time, a specific temperature of the bed, or for example, until it is completely dried up. Now, to validate this model, we'll be doing some additional drying experiments. We'll be doing 1 with the beam down prototype that I previously mentioned, and 3 with a CPC concentrator and with a shallower bed. Here you can see a picture of the concentrator and the geometric concentration ratio that it can achieve. And here you can see a picture of the particles in our beam down prototype. And to measure the water evaporation and the temperature evolution, we'll be using first a precision scale that you can see in the figure that's located directly beneath the particles, and some thermocouples that are located in the inside of the bed at different heights. And the particles that we're going to be drying are going to be of dolomitic lime, which represent the asphalt aggregates, which will be falling in this lower range of the different aggregate sizes. In our case, you can see in the table of the bottom right the average properties of the particles that we analyzed. Now, comparing the experimental results with the simulations, here you can see the first results of the beam down reflector. In this case, we had a higher mass, higher water content, and higher concentration. And you can see how the dotted line that represents the simulation results follows closely both in terms of temperature and in terms of water evaporation. In the temperature comparison, you can see that it follows the average temperature, and it's located within the range established by the standard deviation between all the measurements of the temperature. And on the picture of the right, you can see that we did not reach complete drying of the particles in these tests. That's why we also performed the other test with the CPC, which you can see in this figure. In this case, we have lower mass because the bed is more shallow. We have lower water content and also lower concentration. And you can see that the temperature also falls within the standard deviation range, and on the other hand, in this case, we were able to completely dry up the particles. You can also see that there's a lot of noise because during that day there was a lot of wind during the tests, so we also had to take that into account. And for this case, we were able to completely dry the particles in less than 30 minutes, which, considering the amount of concentration we had, I think it's a pretty good result. Now, if we wanted to extrapolate these results up to a bigger scale and analyze what is better in terms of concentration regarding the depth of the bed, you can see in the figures of the top the drying times of different moisture initial water content, and in the figures of the bottom, the mass process rate, which means how much mass we can process in terms of both bed depth and incoming heat flux, which is the concentration. And one can think that maybe having a deeper bed, but that takes a little bit of more time to dry up, would be better to process more materials than having a completely shallow bed. But in this case, the results tell us the opposite, that it's better to have a shallow bed and process it multiple times to obtain higher mass processing rates. Now, rounding up this chapter, we were able to develop an iterative model that simulates the drying and heating of these fixed particle beds with incoming solar concentration. We obtain experimental results where we were able to dry a 9 millimeter deep bed with 2.56% water content in less than 30 minutes, which means that this approach is viable to dry these particle materials. And also, we have established that the depth of the bed is a more influential parameter than the heat concentration that we can obtain above it. So, moving forward to the last chapter, here we'll be doing the final step with this technology, which means we're going to be bringing the technology from the paper which we started in our PhD thesis up to a commercial scale, which means we'll be building a beam down reflector of almost 2 meters above the primary mirror line, which is a big step in this, taking this technology closer towards industrial or commercial level. This could only be done because of the generosity of Solatom, which offered us their solar field to do this test and construct this prototype and obtain these results that I'm going to present to you now. Here you can see a picture of the Solatom solar field that they sell. They're compact models that you can move them around as a container and then open them up to obtain the solar field. And the tests were done in a special prototype that they had in Universidad Politécnica de Valencia, which consisted in 2 of the prototypes in the middle, connected with an intermediate section, as you can see in the figure of the right. In this case, as the solar field was completely predefined, we could not design the primary mirror field, nor the focal height. So those are input parameters. Also the width and the curvature. The only thing that we could work with is the beam down fraction once again. That's the beam down height related to the focal point. And it is, in this case, we analyze them between 0.51 to 0.75. And here you can see the basic results of we obtained with varying this range for the solar field that they had. You can see a similar trend than the results I previously mentioned, but in this case, the best concentration ratio results in using 70 mirrors of 3.2 centimeters wide, which is not as viable as a construction-wise. So in order to solve this, we changed the beam down width for the mirrors, and we are gonna use 15 centimeters wide mirror. As you can see, there's some decreasing in the performance of the solar field regarding the 70 mirrors, but the trend is also similar. And in our case, we're going to be focusing or developing the solar field for a BDF of 0.7, which means 7% of the focal height, which may not yield the best concentration, but falls in a good range between both concentration and the power we can obtain per meter long of the solar field, which is a good intermediate point. Here you can see a sketch of the solar field that we had and then we modified, and you can see first that the 2 mirrors in the center, we had to take them away because we needed some space to first construct the beam down and then to locate the solar receiver that we're going to be using. And additionally, you can see some of the measurements. First, the beam down is located more than 2 meters above the primary mirror field. The beam down is around 1.6 meters wide, a little bit more. And the orientation, it's not in this case north to south, but almost east to west. And this means that the expected results using a north to south orientation drop down almost 30%, 13% for the solar solstice of the summer solstice, sorry. Now, to take the measurements, once we have constructed the solar field, once again we will be using the camera and the Lambertian target with the radiometer located in the receiver region. And here you can see a picture of the solar field in the day of the test. Several things we have to take into account. We lost this mirror because of hailstorm damage that some days before the test, it hailed in Valencia and it was lost. However, it doesn't affect the measurements we took because the projection of it through the beam down doesn't reach the solar receiver. But also we have to, the line numbers 9 and 1 were not working properly, so we couldn't use them for the test. So instead, we had less mirrors to actually concentrate the solar irradiance. Now, for the positions that we had the solar field when taking the measurements, we once again analyze them using the simulation software. And here you can see that we have basically two different concentration sites. If we focus on the left, that's the one where the Lambertian target is located. We can compare it with the actual measurements of it. And you can see that the results are fairly similar between both the simulation and the measurements. And if we were to express these results in terms of a curve, you can see here that in the left side of or the left normal distribution falls similarly between the Lambertian targets, that's the one in the dashed line, and the simulation results, that's the one in the continuous line. However, we have to ponder why does the design ideal concentration, instead of following a normal distribution, falls between two. And this is basically because of, well, construction errors, that being a bigger scale, everything's magnified, and all of these smaller errors become more impactful, and also because of tracking errors that may have hindered us in the tracking process. Now, finally, rounding up this technology, this chapter, sorry, we were able to commercially adapt adapt a commercial solar field that already existed into a beam down, and we were able to obtain the first experimental measurements of this bigger scale solar prototype, and also to, well, highlight the importance of a precise construction of this technology. Now, finally, rounding up this presentation and this PhD thesis, we can come to some general conclusions. In this process, we started up by doing some ideal design process, obtaining the best relationship ratios for the solar field geometry, and obtaining the theoretical concentration that we can obtain. With these results, we were able to develop a prototype, construct it, and obtain the first experimental measurements with it. We also were able to perform an environmental analysis, obtaining a reduction in GWP. We also developed a concentration solar drying model for a particle bed with concentrated solar irradiance, and we were able to bring up this technology up to a commercial level, from paper to commercial level during this PhD thesis. So, is it viable? Technically, yes. We were able to dry the particles, we were able to concentrate the solar heat, and obtain reasonable drying times. However, there's still more that has to be done, because all of this was, well, done in a more focused point and in a more smaller scale. So we also have to take into account that for industrial processes, these particles would be moving, so we want to also develop a model that considers this, as well as perform some tests with these vibrating beds that move the particles. And we also want to reduce the shading casted by the beam down. That's one of the main drawbacks of this technology, so we have to explore more beam down approaches, maybe using also this flat beam down design, but modifying it a little bit. And also, and more important, perform an economic analysis, because even though it might be technically viable, it doesn't mean that it is commercially viable. So we want to analyze this in terms to finally know if this could reach industry or not. So we were able to obtain good results, and that's my presentation for today. Thank you all for coming, and I hope you enjoyed it.
Thank you very much. Okay, thank you very much again, and now it's time for questions. So we'll start with the Secretary of the committee.
Thank you. Can you hear me? Yes. Well, first of all, I would like to thank to University Carlos III of Madrid for inviting me to take part as this thesis jury. Thank you very much, because it's a really interesting work. So, and secondly, I would like to congratulate Sebastián, the PhD candidate, for his extraordinary work. I like very much the work, so thank you.
Thank you.
And the presentation. So I have only a few questions about the beam-down prototype. The first one is about the secondary reflector.
Yes.
Yes, no, it's okay. The secondary reflector consists of several flat mirrors at the same height, okay? Have you considered to place these mirrors at different heights to follow a hyperbolic shape? Do you know?
Yeah, we also considered that
yes.
in a previous work, and we also obtained good results in terms of well, concentration and comparing it with a hyperbolic complete mirror.
Yes.
But also it comes with the issue that in this case it's easier to place all of the mirrors at the same height. We only have to build like one surface
support.
that's located,
Yes.
and each of the mirrors will have their own. In one of the pictures you could see, like we designed this placement board, you could call it, which has all of the different inclinations of them.
Yes.
So we just take them, put them in, and they are set to go. In that approach, I think it would be harder to position them following the hyperbolic shape properly.
Okay. But you are thinking about this in the future or not? Or there are many complications to put these mirrors at different heights? Do you know?
No, we're considering using mirrors at different heights, but not following like the same hyperbola.
Okay.
We're taking a new approach that we'll still have some work to do in the future with it.
Okay.
But we're also considering them instead of making them all at the same height, using some inclination with them. So
Because by doing so, the secondary reflector width will be smaller, so the Saturn losses will be smaller. So too. So no, I don't know, but perhaps it's a good option. I don't know. I have another question about the optimization process, because you have optimized in base of the optical efficiency, more or less, no? But have you considered the energy or exergy efficiency? The solar flux in the receiver, because I think this is a hypothesis, I don't know, but I think that if you move the hyperbolic mirror, you have a more spread flux mass.
Yeah. The higher it is, the more spread it is, and that's also
Yes.
because why we had lower concentrations when we increased both
Lower
the focal point
concentrations.
and the beam down.
So there is two approximations. If you want to have higher solar flux, perhaps you have to concentrate in one line, no? But if you want to have a more uniform solar flux, for example, for your application, for the drying process, perhaps, it's important to have two focus lines. I don't know.
Yeah, like a wider channel.
Yes.
Focus. That's one of the things we consider when using when designing the beam down for Solatom.
Okay.
That's one of the reasons also why we chose the 0.7, which did not yield the best concentration, but instead of the 0.6, which yielded.
Yes,
so
you are
that
right.
was like the good compensation between both of them, and because of the concentration distribution profile was more uniform than other approaches. So that's also one of the things that we considered in that design.
So yes, okay. So it's a good option to introduce something like an exergy efficiency or energy efficiency, besides the optical efficiency. I think so.
Okay.
Yes. Another question about all the questions are about the optical simulations. No, not all. About the simulation program developed in MATLAB to simulate the optical behavior of the beam down. So you have developed a simulation program in MATLAB. Yes.
Yeah. Well, it's like within the design process. So,
Yes.
The model developed in MATLAB was used to calculate the positions, to
The
design the solar field
optimization
on
configuration.
Yeah,
The optimal configuration, sorry.
Yeah, and once we have the optical configuration, we use this simplified approach to obtain the concentration and the optical efficiency of the solar field that we have designed, instead of going through the salt trace and setting it up.
Yes.
And to obtain the first, the first rough results, it's fairly good for it. So it simplifies this process.
Yes, that's the question, because in chapter 2 you have validated the simulation program with salt trace, but I think that in chapter 3 you use again salt trace.
In chapter 3, which is chapter the
Sorry.
environmental analysis.
Yes, I think you use salt trace again.
Yeah.
No, but
know.
I am
Yes,
not
yes,
sure.
yes. In the prototype one, when
Yes,
calculating
yes.
the optical efficiencies of the different
Yes,
stages.
exactly. Yes. So why haven't you used your simulation program?
Because the salt trace results are more accurate. My
Yes.
simulation program gives some rough first approach results.
Okay.
But if we want, and also because my program does not tell me the heat flux of the different
solar
stages.
flux map.
So what
Oh.
we did, what I did in salt trace was only to consider, for example, all of the primary mirrors, and only focus on the heat flux that reaches these primary mirrors, and afterwards the same, but with the beam down reflector, and like this discretization and like focus on these different sections. I couldn't have done it in my prototype or in my design methodology.
In your simulation
No.
program. Okay, that's the question. And then only one thing more. It's about the convection heat losses in the drying process.
Yeah.
You have used Macadam correlations for natural convection.
Yes.
Yes. Why haven't you considered the windy situation, a forced convection with another correlation, or it is not necessary?
Not yet, but it's for the next step. As we want to, for example, move the particles, then we will have some forced convection, and that's like for the next step. In this first approach is more simplified and more direct, and only considering the natural convection coefficient. So for the next step of the drying model, where we consider the movement of the particles, we also take into account that.
Okay, thank you. Well, that's all. Thank you very much.
Thank you.
Thank you. Thank you very much. So I will give now the floor to colleague here.
Congratulations. The work is very good. The presentation was clear and concise. Congratulations.
Thank you.
I don't have a question. It's very good.
Okay, thank you very much.
So I will take the floor. Starting with thanks again for inviting me to, maybe we need to switch off one of the two mics, to be here at this interesting, let's say, PhD and general theme that is within my field of expertise as well. I must say that when I read the thesis at home about a month ago, I found it as a very comprehensive work, very well written and documented, and taking and examining the subject from all sides, from all angles. So it's really a very good work. To say the truth, I found the structure a bit strange for a PhD, but maybe it's the standard of this university. I would say a few things. For example, I never see references at the end of each chapter. I never see the chapters to be, let's say, independent one from each other. Usually it's not. And also nomenclature, individual nomenclature for each chapter. Usually there's one common section, usually in the front, the nomenclature and for the whole thesis. But okay, as long as it is following the whole thesis, it's not a problem, provided that this is the standard of this university as well. No problem about that. Some of the references were written in a wrong way, to my opinion. For example, when you have more than 3 authors, you don't use all the surnames. You just put a DAL, which is the simplified, the Latin for and others. I have marked all these on the document I will give you afterwards, and some other questions. I have a lot of questions. Most of them were solved in the presentation, to say the truth. So I will ask a few general questions. Before I do this, let me see if I have anything else written. There is a drastic change between the rest of the chapter and chapter 1. Chapter 1, I don't know, it is as if it's written by somebody else. So I see that you already have a few papers published, which is very nice and very good, and supports a lot the whole thesis, let's say, in that respect. And yeah, some questions I have for various figures I think were answered from your presentation, so I will not go directly to them. Maybe a few general things that I noticed also from the presentation now is the model, the actual model you tried to prove the scaled down model that we have seen in the lab is not a real industrial model. It's in between. I mean, it's not a real industrial size. It's much smaller, although whatever that name is, they take this in containers and put it in certain industry and do some processes. So in that respect, it is a real commercial plant, but the real power plants, let's say, of these technologies are much bigger, of course. So do you expect any problems in this bigger upscale, especially with respect to flat mirrors, which is, okay, one disadvantage, a small one. I know Fresnel, when designed the first collector and broke down actually a parabola into small strips, and once the strips follow the parabolic shape, then the strips can be flat. No problem about that, provided they are narrow. But as you go in a bigger scale, the weight gets much bigger, so you have a much more radiation spillage, I would say, which could create problems in that case. Can you elaborate a little bit on this?
Yeah, well, of course, there's several parameters that we have also to consider when developing longer processing lines as well as bigger scale in terms of width, being one of them. Well, that of the height, that the construction would be higher, and we'll have probably to segment it in different stages because, well, it would require a bigger structure-wise. In terms of the losses, well, it depends on the solar field configuration. The wider the solar field is, the more beam down height, beam down width we would require, and it also has to be compensated with the height that we located. Take into account that the higher it is, the more narrow it will be. So if we weren't to design a complete solar field, but to readapt a bigger existing one, we have to take that into account. Where, how wide is it? Where is the focal height located? Where do we obtain the best positioning of the mirrors in terms of concentration, in terms of optical efficiency, sorry, in terms of the costs, because the lower it is, the bigger the structure has to be in terms of width, which also increases the shading. So all of those details, if we were readapting a solar field, have to be taken into account.
Okay. Also, one suggestion I have concerning the base where you have the material to dry. Maybe there is a good idea to put some kind of lips, I would say, of parabolic shape. So any stray rays that may be reflected from somewhere else can be easily concentrated back to the basic,
like a third concentrator.
Like a CPC concentrator, but not of a very big height, so as not to create problems to the other mirrors. But maybe a little bit, so as to have a little larger area, so as to get all those stray reflections that may happen in a real field.
That could also be an interesting approach. We also have to consider, at least for the fixed bed, the effects it would have in the natural convection coefficient, because it may hinder it a little bit because of we're restricting the sides of it where like the fresh air comes into. So that will also have to analyze. But if we were to have a linear approach where we have moving particles, I think it could be a good approach to take into account.
Okay, thanks. And a final question is, okay, you develop this technology. What is the future of it? I mean, where else can be applied? What other processes can be involved into this kind of design, of the concentrator?
You mean in terms of
actual applications?
Applications. Some of the approaches we took apart from the asphalt industry, that's like our main target for the moment. We also consider the gypsum industry, where we have to dry gypsum, and also the copper concentrate.
The what?
Copper concentrate production. Copper concentrate, usually when it comes from the copper ore, it has around 0.5% in copper, and it has to be increased in terms of purity using a process that leaves the copper concentrate with a high concentration, with a high percentage of water content, and almost 75%, and it has to be dried down to around 8% before shipping. So we think maybe there we could also have an approach. But in theory, this is designed for particular materials that have to be dried. It could also, in theory...
Away from drying, have been maybe for other industrial processes, like industrial process heat, for example, can be...
It depends, because...
or the whole idea is just to reflect down.
Yeah, because otherwise, I mean, the drawback that we're assuming adding the beam down is because we want to process heavier materials. If it weren't heavy, if they were light, for example, we could process them with a standard linear Fresnel. So that's one of the the main approach we took, is to process heavier materials.
Can the receiver, the final receiver, can be a pond of sorted molds, for example, and keep it as a source of heat and maybe pass through pipes water to make it steam or whatever.
It could be.
And instead of having up there, it's much better to be on the floor, of course.
Also.
Yeah.
Yeah, I mean, in theory, it could work with any material you want to process, if you want to supply heat closer to the ground level.
Yeah, thanks a lot. We'll now open the floor for questions from the audience. Yes, please, you'll take care of it.